take all this batting data and I say, let's take the years 2010 to 2018, and we're going to use a regression to predict batting average based on lag batting average and career batting average. And then we'll throw in some other things as well. So I'm going to narrow down my batting set. Instead of the whole history, I'm going to take batting, and I'm going to filter for year ID greater than 2019. And one of the things I'm going to do when I do these factor variables, there are only a few players in this frame that are 19, 20, and 21. So I want to put them in a category that very well, or the regression can't work very well that way. So I'm going to lump all the guys in that are under 22 into call them 22, and all the guys greater than 40 I'm going to call 40. Otherwise, I'm going to keep them at their original age. So I'm going to run that. And then here I'm going to omit any observations that have NA values. So if we think about it, somebody in their first year doesn't have a lag batting average. Right? Somebody in their second batting year doesn't have a lag 2 batting average. So we're going to omit all those variables. And so we're going to be left with 1,500, or nearly 1,500 observations for this period. Then I'm going to convert year ID and age into factors. And what this will do is essentially allow us to create dummy variables in our regression without specifically naming each one of those. So let's run that. I'm going to create factors for year ID and batting average. And now I'm going to run my regression. So just like we've done before, I'm going to have this object linFit, and linFit is going to contain the results of this linear model. In the linear model, I'm going to have batting average as my dependent variable. That's what I'm trying to explain based on lag batting average, last year's batting average, 2 years ago batting average, and the career batting average up to 2017. The data set I'm going to use, again, is this batting 2010. So let's run that. So it runs, and let's summarize and look at the results down here. So here are my results, and we can see that R squared, or adjusted R squared, is about 2.26. So we're really only explaining about 26% of the volatility, or we're only explaining about 26% of what goes on with batting average based on these. So how do we think about this? So we would say, how do we get a forecast for a guy's batting average? Well, we take 0.07 plus whatever his last year batting average is, times 0.245, plus whatever it was the year before, times 0.171, plus whatever last year's career batting average was, times 0.275. We see that all of these variables are statistically significant. They all have explanatory power, but the regression doesn't explain that much overall. So that's one formulation we're going to use. And then this second, we're going to say, well, one of the things we think about that might be important is what year. Some years it was easier to have a high batting average, some years it wasn't. So essentially we're going to use dummy variables for year, and we're going to use dummy variable for age, because we think, well, gosh, there's probably at certain ages guys improve, certain years guys decline. So let's run that and then summarize those results. So let's take a look at the results here. And here we have it. So notice we get somewhat different intercepts. Let's look down here at our adjusted R squared. Notice we get almost double the explanatory power. Almost double the explanatory power. And what do we find here? Every age after 22, we actually see a decline in batting average. Now, some of that is sample skew, because if you think about these guys that are in the league before they're when they're 22 or below, all these guys are in the intercept, right? So that's part of the intercept, essentially is a positive compared to the age that's a positive in the intercept. All of these bring the batting average down. We see no statistical significance for the years, but we see, so maybe we want to run it without the years and just the age, but we're going to stop there and keep it as it is. All right. So now how do I use to fit the data? So first I'm going to fit the data, and basically what I'm going to do is say, well, okay, Joey Votto, we know what he hit in 2018, but this model is going to make a prediction for, this regression model is going to make a prediction for what the regression would say his value would be for 2018. Okay, so we're going to fit each model and put it in a new variable in batting 2010 called fitted 1 and fitted 2. So let's run that. So the predict is going to take the first model and fit it to batting 2010. So let's run that. Let's run both these and take a look at batting 2010. And let's go out here to the end, and we can see that, so this first guy, Bobby Abreu, his, let's take a look. Bobby Abreu's batting average in 2018 was 250, about 255. 255. The first regression fits says his, that year based on the model, his batting average should have been 283, and the second model should have been 274. So the difference between the fitted value and the observed is the error in that regression. How much of an error there is for Bobby Abreu, the prediction for Bobby Abreu. And we see all of these, we're going to see there's some kind of difference between all of these fitted observations and what they actually hit during the year. What a regression essentially does is try to minimize the sum of those squared errors, right? So to try to make those squared errors as small as possible. So both models are going to give us a different prediction. We would think the second fitted model would be a much better fit for most guys because so much more is explained as observed by the adjusted R squared.